Washington State University. Go Cougs!
Welcome back to our course on statistical inference. We're in Module 3, where we are discussing dimensionality reduction and clustering. And in Part 3 of this module, we'll be looking closer at clustering. Clustering is usually referred to as an unsupervised learning method, mainly because it doesn't take the class values into account. So for example, in our sensor data, we would just be looking at the 9 sensor feature values and not necessarily including the class values of work and play in our analysis. So we may want to generate something like this, which is a clustering of our 56 sensor data points into 3 different groups. Again, we're looking to understand better the major trends of the data, specifically how some groups, subsets of the data may be close to each other, but dissimilar from other groups. Now, there are many different clustering techniques, and many of them within scikit-learn, but one of the more popular techniques is the k-means clustering technique. And this is the main approach for doing k-means clustering. So the idea is that we choose a value for k, and that's how many clusters we want. So in this picture, we chose k equal to 3. And in the k-means clustering approach, the first thing it does is it chooses k seeds to start with. And there's a variety of ways to choose those k seeds. That's why the choose word is in red. That's a parameter to the system. But we'll be using the default approach, which is kind of an intelligent way to choose points that are well distributed across the feature space. The next step then, once we choose our seeds, is to partition all of the remaining points into the partition of the seed they're closest to. And so to do that, we need some way to compute a distance between two different points. And again, this distance computation is in red because that is a parameter and sometimes can even be a customized distance measure for your particular domain. But in our case, all of our sensor data are real values, and so we're going to essentially use the Euclidean distance in order to implement our distance metric. Now, as a side, when we do use Euclidean distance, one of the downfalls of that is that if some of our features have a much larger range than others, then they will tend to dominate the distance. And so as we'll see, we're going to use the scale preprocessing technique to scale all of our data down so that it all has about the same range, and that will improve our clustering results. Okay, so we choose our seeds, we partition all the points up into the group with the closest seed, but then we recompute our seeds by moving them toward the centroids, or the center of the points that were in their partition to begin with. And then we repeat that. So we again partition the points up to their closest seed, we recompute the seeds, repartition the points, and continue that until the seeds settle down and converge and don't move as much. So to give you a little better idea of how this works, here's a simple example where we have our points are represented by the blue dots and the blue circles. And to begin with, we're going to do k-means clustering for k equal to 2. So we have 2 seeds, those are our x's. And so the first step is we put each of the points into the partition of its closest seed. So these 2 points up here, one of them is right on top of our seed, the other one is a little bit below and to the right, but those 2 points will be partitioned with the upper right x seed. All the other points, the dots, will be partitioned closest to this lower x. Then for the next iteration, then we recompute the seeds. So this seed here will move into the middle between these two circles. And then this seed will move a little bit further into the middle of these points. And so now we've computed our seeds, and then we go back through the points and we put them in the partition of the seed they're closest to. So you can see this brings in a few more of the points into this upper right partition. And we continue iterating in this way. Again, we move the x's closer to the centroid of the points in their partition, and then we repartition the points to their closest seed. And continue that. And so again, once the seeds tend to settle and don't move much anymore, our clustering is complete, and we can identify all of the points in each of the clusters, and hopefully that'll give us some more insights into the data itself. Okay, so let's look at the actual code for doing this. So this is the cluster Python file, and a few explanations here. So we're still going to be reading in our data as usual. We're going to be using some of the array manipulation techniques that are in the NumPy, the numeric Python library. As we mentioned, we're also going to be scaling our data, which improves the clustering a bit. So from the pre-processing module, we'll load the scale method, and in order to project our 9-dimensional data down to 2 dimensions for better visualization, we'll use the PCA approach we learned about earlier in this module. And then finally, we'll load in the actual clustering technique that comes from the cluster module, and we're using the k-means cluster. And also the matplotlib will allow us to visualize the results. Now the k-means cluster again has many parameters, but the one that we're most interested in for now is just how many clusters we want, the value of k. We'll choose a value of 10 initially for that. And so then the next step is to read in our data as usual, but again, since we're not interested in the class values, we're only going to read in the 9 sensor data dimensions. And since we're only interested in those, we can read it in a little bit more efficient, more Python-ish method, and that's using this zip method. And what zip does is, again, we've read all of the yaw values into this yaw variable, all of the pitch values into the pitch variable, or it's a list. And so what zip does is it will go through and create lists based on the same index of values in each of these variables. So the first list in X will be the first yaw value plus the first pitch value plus the first roll value, etc. The second list that this produces will be the second yaw value, the second pitch value, the second roll value, etc. So when we're all done, X will contain the same results. It will contain our feature vectors for each example. But again, this is a slightly nicer way to do it that makes the code a little easier to read. Then the next step is to actually do the clustering, but we have a few preliminaries first. First, we're going to scale our data. So we'll transform X into scaled data. Again, the purpose here is to scale the dimensions so that they all have about the same variance. Next, we're going to use PCA to transform our data to project it from 9 dimensions down to 2, mostly just for visualization. So we create a instance of the PCA class saying we want 2 dimensions. We then use a kind of a combine, instead of doing a fit followed by a transform, the dimensionality reduction techniques have one method called fit transform that essentially does both in one step. So to the scaled data, we've used PCA to identify the 2 high variance dimensions, and then we transform that scaled data to those 2 dimensions, and that gives us our 2D data. So this is the data that will actually cluster. The K means cluster. We create that and pass in the number of clusters that we want, in this case 10, and then we fit the cluster to the data, which effectively clusters it. I do want to mention that we could, of course, do the clustering on our 9-dimensional data and then project the 9-dimensional clustering down to a 2-dimensional clustering. This approach is a little bit more efficient because the clustering is operating on fewer dimensions, and typically we get about the same result anyway. So we tend to project the data down to 2 dimensions first before we do the clustering. Lastly, we want to visualize the results, and this should look similar if you remember the module we did where we looked at the nearest neighbor classifier, and we actually visualized the different regions of the neighbors around the points. We used a similar technique, and again, just very briefly, what we're doing here is we're creating a grid pattern over the entire space of our data, and we're coloring each of those grid locations according to what partition they are in, and we choose a different color for each one. And then down here, we're actually plotting our original points so we can see where they fall within the different clusterings. So again, I won't spend much time on that. That's code that's pretty much available on the scikit-learn page that you can use to colorize your own clusterings. Okay, so let's run this and see what we get. So again, this is the cluster.py file, and actually just to double check, I want to make sure that I have it set to 10. Yeah, so we have the number of clusters set to 10 here. So we'll run that. Okay, and so there's our clustering of the sensor data points into 10 different partitions. Again, some of the partitions actually just have 1 point in them, so probably 10 is a bit overkill for this. We can kind of see there's maybe 4 to 3 different prominent regions, this middle one here, and then a couple of outliers over here and some over here. So we might want to take a look at maybe a clustering of 3 and see if that gives us a little bit better look. So let me go back into the code and change our 10 to a 3 here. And we'll run that. And so here's the clustering into 3, and we actually already saw this picture earlier in this part. But as you can see, there's still this one outlier up here, and everything else kind of falls nicely within these 2 clusters. Now again, we're not looking at the classes. There may be a mixture of work and play here and a mixture here, not to mention the fact that these are actually projected points down to 2 dimensions. So the actual dimensions we're looking at aren't, say, acceleration or rotation or yaw, pitch, and roll. There's some linear combination of those. But anyway, the point is that we see that our data is kind of grouped into 2 or 3 major groups, and that just gives us some more insight into the behavior of the data that we're looking at. Okay, so go back to the notes. So in this last slide, I put together several different clusters for different values of k. Here's the k equals 10 and k equals 3. I also have one for k equals 5 and one for k equals 2. So again, you can play around with different settings, different parameter settings for the clustering algorithm, and you can try other clustering algorithms as well, again, to try to get a better insight into the general patterns that are in the data. So in review for the module we've been looking at, we first started out looking at some dimensionality reduction techniques for reducing the number of dimensions. One approach is feature selection, where we're essentially eliminating features that aren't helping. And principal component analysis, we're actually computing new features that have high variance and typically much fewer features, so that if we have a high dimensional problem, we can convert it to a lower dimensional problem, which generally improves the performance of our statistical inference. Lastly, we looked at clustering, and specifically the k-means clustering algorithm. Again, that's designed to just give us a view of our data and help us to identify some of the major trends in the data. So that completes Module 3. Congratulations. And now we have a few more tools to add to our toolkit to help us perform inference on our data. And so these should help give you a better way to understand and learn from any sensor-based behavioral health data that you're collecting.